Okay, I want to go through this position time graph. So I've set up a little demonstration which is about the same as what I did in class. And here I have a train which starts at the position which I'm going to call 0, just because I put my meter stick here and I set 0 to be at the point where the train starts. Now the train is going to roll. I'm going to give the train just a tiny little push. It's going to roll down the hill, and it's going to wobble back and forth like that. Okay. Now I can see that its position is changing. It goes forward up here, and then it rolls back, and then it rolls back a couple more times, and then it stops. Okay. So its position goes from 0 to maybe about 35 or 36, and then back to about 20, and then back to about 30, and then back, and it finally ends at about 25. Okay, now I can put that on a graph, but in order to make a graph I need two axes. I need a position, and for my other axis I'm going to use time. And I can measure the time just by pushing start on this timer. It may be hard to see this timer on the video, but you can imagine what it's doing. I'll count it. 1, 2, 3, and so on. Okay, so I was just counting the seconds. 1, 2, 3, and so on. So it takes about half a second to go over here, and then maybe 1 second to get back. Once it comes to go back over here, and then by 2 seconds it's already completely stopped. Okay, so how can I make a graph like this? Well, first, for the position time graph, I'm going to do position versus time. Position's on the vertical axis, time's on the horizontal axis. And I start the train at time 0. The time is reading 0 when I start it. And it starts at a position which is 0. Okay, I did that just to make it easy for myself. So there's my 0 position time. Now the train rolls down the hill and then gets to a point which is maybe partway up the other side, and I say that's about 35 centimeters. So let me make another point. So that's the farthest away it's going to go. So I'll put 35 centimeters here on my graph. Okay, now what about, now how long does it take to get there? Well, I said it would take about half a second. So I think I'll make marks for seconds. 1 second, 2 seconds, like that. And it got to 35 centimeters in about half a second, so that's about here, half a second. So, it probably did something like that. And then he turns around and comes back. He rolls back, let's see, how far does he roll back? He rolls back to about 20, about 15. So let's put a mark here for 15. And it takes him about a second to roll all the way back there. So there's another mark. I think I'll make this curve a different color to be clear. Different colors here. So he started out moving a little slow, and then he sped up and went pretty fast as he was going down the bottom. Then he slowed down as he went up the other hill, so the slope is changing. And then he came backwards through this way, and so here he had a very high velocity. He was going backwards. Then he stopped, and he went, what happened there? Looks like he went back over to about maybe 30, something like that. Okay, so you can imagine the train starts at the top of the hill here, goes all the way up, part way up the other side of the hill, turns around, comes back, turns around again, comes back here, turns around again, comes back there, and then finally stops. And the whole thing takes only about 2 seconds, right, from beginning to end. So it's like that. Okay? So that's the idea of the position time graph. Now there are a few things you can see on it right away. One is you can see the velocity at any time in this whole thing. The velocity is the slope. on a position-time graph. Okay? Remember, velocity is equal to change in position over change in time. Okay? So the change in position over change in time is the slope anywhere on this graph. So for example, there's a very high velocity here. Here the slope is very steep. So this is the maximum in this whole thing. Maximum velocity. Here, what's the velocity? Well, here it's 0 because the slope is 0. It's not moving. So you could say that when the train gets up to its stopping point here, it's moving in a positive, it's got a positive velocity as it goes up, and it stops and it has 0 velocity momentarily, and then it starts rolling back. So then it has a negative velocity here. Velocity is less than 0 there. Here, the velocity again is 0. Then, so that's when he stops going partway back up the hill over here. So again, that's here. That's this point here. Velocity is 0 again. And then as he's going back down through the bottom, whoop, again, he's got a positive velocity there. So here the velocity is again greater than 0. So it's positive here. So anytime you have a slope that's pointing up that way, there's a rise over the run, is positive, then you have a positive velocity. Here the fastest velocity was the first time he rolled down the hill, as he went through the bottom here. See, right, when he went through the bottom, that was when he was moving fastest. And he came back, every time he went back through, he was moving slower. So this time, here the slope here is smaller than the slope there. This is not as steep a line as that one is. And that shows that the velocity here was less than the velocity there. The velocity keeps decreasing until you get to the end.